Hello everyone, in this video we will cover the following topics steps by steps. Determining the maximum factor design moment, designing the reinforced concrete beam for longitudinal tension reinforcement, designing the shear reinforcement and calculating the required stirrup spacing. So let's get started. A simple supported beam with a span of 25 feet is subjected to a uniformly distributed dead load of 2 kips per foot and a live load of 0.5 kips per foot, along with the concentrated dead load of 2.5 kips and a live load of 1.25 kips applied at the center of the span. The size of the beam is 16 inches by 26 inches. And we are given 60 KSI for yield strength of steel and the concrete strength of 4 KSI. So we are required to determine the maximum factor design moment and the design beams for required longitudinal tension reinforcement and determine the required stirrup spacing for shear reinforcement. So here we have the simply supported beam, 25 feet span. And we have the dead load of 2 kips per foot, live load of 0.5 kips per foot. So the concentrated load, we have the dead load of 2.5 kips and a live load of 1.25 kips. So we have the cross-sectional area of the beam, we have 16 inches wide and the total depth of the beam is 26 inches. So we have a provision in the code, table 9.3.1.1, that the minimum depth requirements for simply supported beams should not be less than to L over 16. So it should be greater than or equal to L over 16. So if we have 25 feet span over 16, that would give us 1.5656 feet, or equal to 18.75 inches, which is less than to 26 inches deep beam, the one that we have assumed. So let's get started with the solution. First, we need to determine the factored uniform load. So the factored uniform load, the self-weight of the beam is already included in the dead load. So W sub U is equal to 1.2 times 2 kips per foot plus 1.6 times 0.5 kips per foot, and that is equal to 3.2 kips per foot. So the factored concentrated load, which is this one here, that is P sub U is equal to 1.2 times 2.5 kips plus 1.6 times 1.25 kips, that is equal to 5 kips. So that is the factored concentrated load. So we have already determined the uniform load and the concentrated load, so we can now proceed to calculate the required maximum factored moment. So the factored moment here is a total is equal to WL squared over 8 plus PL over 4. So this formula is uniform and this one is concentrated. So that is equal to 3.2 times 25 feet squared over 8 plus 5 times 25 feet over 4. So the total maximum factored moment is equal to 3,375 kip inches. So we can now proceed to determine the required tension reinforcement. So here, determine the steel reinforcement. So we need to determine the steel ratio first using the given formula. Assume tension control. So we have to assume that Fs is equal to Fi, so that P is equal to 0.9. Then we can estimate the effective depth of the beam, which is equal to D equal to 26 minus 1.6 inch the cover, concrete cover, minus 0.5, assuming that we are going to use the 1 inch diameter main reinforcing bars, and that is equal to 24 inch. So by using this flexural formula, we have the parameter of M and Rn, so that we can calculate the steel ratio. We have M and Rn parameter here, and we will plug in that later once we determine the value. So here M is equal to 60 over 0.85 times 4, that is strength of concrete, that is equal to 17.65. So the Rn is equal to moment over P times BD squared. So 3,375 all over 0.9 times 16 times 24 squared, and that is equal to 0.407. So we have already determined the value of M and Rn. Then we can plug it here in this formula. We have steel ratio is equal to 1 over 17.65 times 1 minus the square root of 1 minus 2m times the Rn, which is 0.407 over 60. So the value of rho, that is equal to 0.0072. Now we need to check the minimum rho requirements as per the ACI 318 section 9.6.1.2. So the first provision for that minimum requirements is equal to 200 over Fy, and that is equal to 200 over 60,000 PSI, equal to 0.0033, and this is the minimum, which is less than to our actual rho, 0.0072. And there is another provision, which is 3 times the square root of Fc prime over Fy, and that is equal to 3 times the square root of concrete strength, which is 4,000 over 60,000 for the yield strength, is equal to 0.0032. So we are above from the minimum requirements. So ES is equal to rho BD. Rho is equal to 0.0072 times the width of the beam times the depth, which is 24 inches. So the required steel reinforcement is equal to 2.76 square inch. So that is our requirement. So if we use the number 8 bars, 1 inch diameter, so we need 4. So 4 times 0.79, the area of number 8 bars is 0.79, and that is equal to 3.16 square inch, which is greater than to what we have here, 2.76 square inch, the required reinforcement. So this is our beam, cross-sectional cross-section of the beam. We have 16 inches, and we have the effective depth of 24 inches, concrete cover a total of 2 inches. So we have here the bar arrangement. We need 4 for using number 8 bars. And do not confuse with this 2 here, because it is not calculated. This is the representation of the hanging bars above in order to tie our stirrups. So now we need to determine the steel strain to confirm whether the assumed Fy is yield or not. So by determining that steel strain, we need to calculate first the value of A, which is this one here, and the formula is equal to ES times Fy all over 0.85 Fc prime times B. So that is equal to 2.76 times 60 KSI all over to 0.85 times 4 KSI times 16 inches, and that is equal to 3.04 inch. So next we need to calculate the C, the value of C, the location of neutral axis, because we have already determined the value of A. So C is equal to A over 0.85, that is equal to 3.04 inch over 0.85, and that is equal to 3.58 inch. That is the location of our neutral axis. So to determine the net tensile strain by ratio and proportion, this one here, if you calculate this one from this ratio and proportion E, and that is equal to 0.003 times D minus C all over C, that is equal to 0.003 times 24 inch minus 3.58, which is the value of C, all over 3.58 inches, which is equal to 0.017. So this is concludes that the steel has yield, which is greater than 0.005. So therefore, the tension controlled. So if S is equal to Fy and the P is indeed 0.9, that is the value of P. So that concludes for our solution of a design of beam. Now we can proceed to the design of shear reinforcement or the stirrups. We will determine the spacing of the stirrups for these sections. So we have the beam where we have already reflected the factored W sub U to 3.2, and the factored concentrated load is equal to 5. We have already determined that previously. So the design shear strength, we have to calculate the reaction at point A or point B. So the shear, the maximum shear is 3.2 times 25 feet over 2 plus 5 kips over 2. So we'll just divide that by 2. No need to summing up moment at A because the loads are symmetrical. So we can calculate divide by 2 directly. So that is the maximum shear that we have here. So the stirrups are not required if BU is less than half of the concrete strength, shear strength, concrete shear strength, that is according to the ACI code 9.6.3.1. So we have to calculate the concrete shear strength, which is equal to P times 2 times lambda times the square root of FC prime times B width times the depth. That is according to the ACI table 22.551. So the PBC is equal to 0.75 times 2 times 1. And this is it is the normal weight concrete, that is lambda is equal to 1. So square root of 4,000 psi strength of concrete times 16 inches for the width of the beam times 24 inches equal to 36,429 pounds. So half of that value, that is 36,429 divided by 2, that would give us 18,215 pounds, which is less than to 36,429 pounds, this one. So therefore, stirrups are required. Now we will calculate the stirrups spacing. So therefore, spacing using number 3 bars, the area of that is 0.11 square inch stirrups, assuming that we are using 2 legs. This one, 2 legs. So the BS can be calculated from this equation here, BU minus PBC all over P. P here is 0.75 for shear, is equal to 42,500, which is BU, minus 36,429 for BC, all over 0.75, and that is equal to 8,094.7 pounds. So that is the value of BS. So we can now calculate the spacing because we have already determined the value of BS. So the spacing is equal to AB FYT times D all over BS. And that is equal to 2 times 0.11. 2 here because we are using 2 legs. Times 60,000 PSI over 24 inch the depth. No, times 24 inch the depth. All over 8,094.7 pounds. And that would give us the spacing of 39.1 inch. Then we need to calculate the maximum spacing to provide minimum AB. And that is the code requirements based on section 9.6.3.3. So the spacing of this minimum requirement, that is equal to AB times FYT over 0.75 times the square root of FC prime times the width of the beam. And that is equal to 2 times 0.11 square inch times 60,000 PSI all over 0.75 times the square root of 4,000 times 16. And that would give us 17.4 inches. That is the required spacing for this provision here for the equation. So the spacing, another provision is for the minimum is equal to EV times FYT all over 50 times the width of the beam, and that is equal to 2 times 0.11 square inch times 60,000 PSI all over 50 times 16 inches, and that is equal to 16.5 inches. So here we have VS is equal to 8,094.7 pounds, which is less than to 4 square root of 4,000 PSI times 16 times 24 equal to 97,145 pounds, which is less than, our BS is less than 97,140 pounds. So therefore, the maximum spacing is equal to D over 2, which is equal to 12 inches, and this is governed for the spacing of the stirrups. Generally, actually, basically, the shear is not critical for this equation. So, we will use number 3 stirrups at 12 inches on center. So, we have only one spacing here. Actually, 12 inches, that's minimum requirements, maximum requirement spacing. So, this is our sections. We have the number 3 tie at 12 inches on center, and we have 4 number 8 bars. So that's all, guys, and that concludes our solution for the shear reinforcement design. And thank you very much, and if you find this video helpful, please don't forget to like, and see you next time. God bless, and bye-bye.